The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'm presenting on Steve Rowell's behalf. He couldn't travel due to some conference restrictions and things, so I'm sure all of our government employees are familiar with. So I'm going to try to do this justice, and if you have any hard questions, ask Steve. We'll go with that. But so as Ganesh mentioned, my name is Robert Moser. I'm also a researcher in the Geotech and Structures Laboratory. And I'm going to go through some of the work that Steve's done that have been incorporated into Change 1, including use of mechanical couplers. So we'll go through some of the updates in that guidance, and then some of the testing that Steve's done to sort of expand upon some previous work that was done looking at different types of splices, primarily welded splices, at low and intermediate and high strain rates. So a little bit about what we're going to discuss. Some background of some previous work. There was some work done back at ERDIC, or at Waterways Experiment Station, back in the 70s that was incorporated in our existing guidance at that time. But many of those splice systems were based on welds and different types of splices that are kind of irrelevant based on current practice. And so Steve expanded on that with some additional testing that we'll talk about. We'll talk about what the guidance was in the UFC prior to Change 1 that Bill talked about a little bit, and then what that guidance looks like now. And then we'll go through some examples of different mechanical couplers that are out there. They sort of cover the main families of mechanical couplers that are available today, and we'll just go through their performance. So just a quick background, and Bill did a good job covering this. But in Change 1 in our UFC 34002, that incorporated for the first time the implementation or potential use of mechanical couplers for reinforcement. And so it provided a testing protocol and guidance on acceptance limit states for actually using this in practice. So this was implemented in the UFC primarily for to replace lap slice connections, especially in areas where we have heavy reinforcement or larger bars where we have to use mechanical couplers oftentimes to prevent congestion as well as improve economy, in some cases for very large bars. And so this built upon the previous research that was conducted by Flathau. We'll go over that a little bit back in the 70s with new work conducted in the late 2000s that's been published and since incorporated into guidance. And so this expands upon a lot of data that's out there on these mechanical couplers for more normal loading conditions. So there is data out there for using mechanical couplers in quasi-static loading strain rates, up to somewhat intermediate strain rates that might be relevant for seismic type loading conditions or cyclic loads, but there hasn't been any studies until some of the work done here to look at dynamic loading conditions and the behavior of many different types of mechanical couplers. And so that's where this work came in. And as Bill mentioned, it was really to build upon or to allow the applicability of using some of these mechanical couplers to expand upon the original guidance provided in the UFC. And you can see that quoted at the bottom, which states, if you're using a mechanical coupler, it has to develop the same ultimate tensile strength and same ductility as the bar itself. So, if you read that very literally like a lawyer, basically no mechanical coupler that's out there today meets that requirement. So we're going to go through what the actual behavior is and some acceptance limits. So the original research done by Flathau was published in 1971. This was done back at the then Waterways Experiment Station. You can see the title of this report, Dynamic Tests of Large Reinforcing Bar Splices. And I believe this has been made electronic, and you can probably Google it and download it. And so they looked at various splices that were available at that time, focusing on number 11 bars at quasi-static, intermediate, and high rates, just given the limitations of equipment. Looking at grade 60 and grade 75 bars with splices at that time that were primarily based on welded connections. This is the setup. This looks very similar to what we use today. Over in Steve's building, I think it's a 200 hip high rate loader, which is gas driven, and they have high speed cameras and things. This is from the original report, so everything's been updated with new instrumentation and things, but it looks basically the same today, other than it being color. But Other than that, it's basically the same. And so here on the right, you can see a little review of some of the research that was executed by Steve and his group in 2009. That was published in an ERDIC, I believe it's TR-09-8 is the document number. And it's titled High Strain Rate Testing of Mechanical Couplers. And so this sort of replicated the work that was done by Flathow, but looked at a variety of new types of mechanical couplers that are on the market today. And so they focused on number 10 bars, replicated the strain rates that were done in Flathow's study, and then did tests on as-rolled and machine bars, so we have some control sort of baseline results to compare against, and then looked at a variety of these different coupler systems. So upset couplers, grouted sleeves, shear screws, threaded systems, and then threaded bars couplers, so a variety of different ones. Here's a photo of some of the couplers and then the control baseline samples from Flathow's original study. This is just cut out of the original technical report. Here you can see a photo of some of the different systems that Steve and their team examined. The study is a lot more broad than this, but for as far as applicability to UFC, this is the data that this is what it's based on. So a variety of different coupler systems, the tapered thread, upset head, grouted sleeve, shear screw, and then threaded bar coupler. So if we look at that guidance prior to Change 1 made in UFC, again, it requires that if we're going to use mechanical splices of reinforcement, they have to develop basically the same dynamic tensile strength and the same ductility. And so we're going to step through a lot of data and basically look at how that's very difficult and basically impossible to achieve with most of these. Even in a perfect system, they still introduce a defect or discontinuity that makes these systems prone to reducing mechanical properties somewhat. I'm just going to show a few different stress strain curves for some of these different systems. These are all obtained in these dynamic tests, so it's a strain rate of 3 per second. And so you can see these black curves, those are for the baseline material, just the as received, as rolled rod, or reinforcing bars. And so you can see for these particular bars, grade 75 bars, the yield strength is about 80-85 KSI, and you get about 12 to 14% ductility. It's pretty typical. But in the case of this tapered thread coupler, we can see pretty significant reductions in ultimate strength. The ultimate strength in these bars is around 130 KSI, and it reduces in this case to around 105 KSI. And then you also get some pretty significant reductions in ductility. So we go from 12-14% down to less than 3%. I also wanted to note, you can see how most of these failures, they're all associated with the coupler. They're associated with threads in the coupler initiating fracture. For the upset head coupler, most of these test results achieved similar tensile strengths, but you can see that the ductilities varied significantly, and in many cases they were not acceptable. And if we look here at the failure surfaces of these, most of them are also associated with the coupler itself. So in one case we do get the ideal failure. That's this last curve here. So the ideal failure is that you basically get the same tensile strength and same ductility as you get with the control samples. But in many cases we saw the influence of the coupler, and especially heat affected zones near the coupler, jeopardizing the strength and ductility of the bar. In the grouted sleeve coupler, these achieved equivalent tensile strengths, but had some significant reductions in ductility depending again on the failure mode of the bar. And so in ideal cases where we get rebar failure outside of the coupler, we get again acceptable levels of ductility and ultimate strength. But in other cases where either the coupler itself failed, the sleeve as part of the coupler failed, or the rebar just pulled out of the grout sleeve, we get reductions in ductility. The shear screw couplers, these all behaved in a similar fashion, especially at dynamic strain rates. We'll see some actual quantitative results from these. But for all of these tests, we saw significant reductions in tensile strength and ductility, and they were very consistent between each sample, where in general the rebar just pulled out of the coupler at lower strength levels and lower percent elongations. And then finally, and these are the best performing couplers that we found at dynamic loading conditions, were threaded bar couplers. So you can see these stress strain curves almost overlay each other. At least to an experimentalist, those overlay each other. And so we get really similar tensile strengths, similar ductilities, and as you can see here in these triplicate samples, all of them fail outside of the coupler. They fail like they should, and we get good performance. Okay. So some of the data from that, as well as a lot of other testing, was used to be implemented in this Change 1 guidance to allow for, or try to allow for more use of mechanical couplers when needed. And so this is the language of how that was incorporated. So now we have some guidance on how these tests can actually be conducted, which will replicate the work that was done by Steve and his group. So it defines the way the test is conducted, the strain rates that have to be considered, and those are referenced back to that ERDIC TR09-8 with a minimum of 9 tests, so you do triplicate tests at your 3 different strain rates. And so the acceptance limits for this, now we have an actual quantitative ductility limit rather than just saying it has to match the properties of the bar itself. We can reduce that and allow for some reductions in ductility based on the coupler. And so if out of those triplicate tests, all of them have similar tensile strengths and they exceed 3% elongation, you can accept those couplers for use. Now, if 1 out of the 3 actually doesn't meet that 3% strain, we can test 2 additional samples. Those 2 additional samples have to meet the 3% elongation requirement, so a total of 4 out of 5 have to meet the elongation requirement. Otherwise, that coupler is rejected. Okay, so just to show you a few examples of these different systems, and again, these requirements apply at all strain rates. So if it doesn't meet at quasi-static, it's probably not going to meet at dynamic either, but in some cases that doesn't happen. So I just wanted to step through a few examples. We can actually look at some numbers rather than stress strain curves to compare for these. And so first with the tapered thread coupler, and you can see that in this case, in the quasi-static strain rates, these couplers perform very well. You get similar tensile strengths and very similar percent elongations. But as soon as the strain rate increases to intermediate and dynamic strain rates, these properties are jeopardized fairly significantly. So we get reductions, and these the bold lines here on the top, this is for the as-rolled controls, just for comparison. So you can see when we get to the dynamic loading condition, we reduce our tensile strength, and we also get significant reductions in percent elongation. Similar for this upset head coupler that we talked a little bit about, we get fairly good performance if we're looking at quasi-static strain rates, but as we step up to dynamic strain rates, those properties are reduced, both the strength and percent elongation. For the grouted sleeve, even though the failures were probably not ideal, did have acceptable properties at all strain rates. We saw tensile strengths and elongations that were acceptable based on the UFC change 1. And then the shear screw coupler, this didn't actually perform well even in quasi-static conditions. So you can see the results where we've got reductions in tensile strength of the bar and also reductions in ductility, and those extrapolate through all the strain rates that were investigated where we just had pull out of the bar from the coupler. And then finally for this threaded bar coupler, which performed the best out of everything that was investigated. And so you can see in quasi-static, intermediate, and high strain rates, we saw acceptable levels of ultimate strength and percent elongation for all the samples tested. So just some conclusions from that testing that was done. Again, in UFC Change 1, we've incorporated guidance to actually do this testing. We're under the previous testing. If we use the previous criteria, only 2 out of all the modern coupler systems that were investigated would meet those requirements in quasi-static conditions. None of them would meet the requirements in dynamic conditions. So if we look at this Change 1 incorporation in UFC, 1 of the 5 coupler systems that was investigated, that threaded bar system, actually meets those requirements easily. 2 of them had at least 1 test out of the 3 tests that required additional testing, and those were deemed to be adequate. And then 2 out of the 5 systems were deemed to be inadequate and were rejected. No additional testing was required. So how we're going to incorporate this into UFC is, so now we can use mechanical devices, mechanical couplers for connections to replace lap splices in congested zones in reinforced concrete systems, with some provisions based on confinement that needs to be provided by the concrete, especially in areas that are prone to spalling and things of that nature. And so the guidance for actually doing this testing has to be done in our laboratory according to the guidance provided in this TR09-8. And based on some additional testing that Steve and his group actually executed, they've divided that into 2 different size ranges where tests have to be performed depending on when and where the couplers are actually going to be used. Most oftentimes that's going to be on larger bars, but in some cases, may also be applied for smaller bars, especially for retrofit applications and things like that. And so those bars can be tested to determine whether they're applicable, and then the results for that coupler can be basically extrapolated over the other bar sizes in those groups. And then, like anything we would do with a mechanical coupler or lap splice or anything, we try to put it in low stress zones and stagger the locations of couplers because there's still a failure point of weakness and discontinuity. And so we try to do this to help with redundancy considerations.